a fighter jet, and your car all have in common? And no, it's not just that they're all super loud. The real answer is that they all work on this one incredible principle, turning heat, just simple heat, into powerful motion. In this explainer, we're going to pull back the curtain on the physics that makes this whole thing tick.
I mean, really think about that for a second. How do we take the random, chaotic energy of heat and somehow wrangle it into the orderly, powerful force that can move a massive train? It's a transformation that literally built our modern world, and the secret is hiding in one particular field of science.
And that field is thermodynamics. You know, the name itself gives you a huge clue. Thermo means heat, and dynamics is all about motion and power. This is basically the official rulebook for how heat, energy, and work all interact.
Now, like any new topic, this one has its own lingo. So before we jump into the really big, unbreakable laws, let's just quickly nail down a few key terms. That way we're all speaking the same language.
First up, system and surroundings. This sounds fancy, but is super simple. The system is just whatever little slice of the universe we're focusing on. It could be the gas in a car cylinder or even your morning coffee. And everything else? Everything else in the universe? That's the surroundings. It's a simple idea, but drawing that line is absolutely essential. Next, we have thermodynamic equilibrium. This is what happens when a system just settles down. Its temperature and pressure are stable, they aren't changing anymore. You can think of it as the system just being in a state of ultimate chill. This idea of balance is going to be a huge deal for everything else we talk about. Okay, so you have your system, right? Well, it needs to be separated from its surroundings by something, and we just call that a wall. But here's the cool part. Not all walls are created equal. You've got a diathermal wall, which lets heat just pass right on through. Think of your average coffee mug. Then you have an adiabatic wall. This one's an insulator. It blocks heat, just like a good thermos. And you better believe this difference is going to be super important. All right, we've got the vocabulary down, so let's get to the main event, the fundamental, unbreakable rules that tell energy what it can and can't do anywhere in the universe. Let's talk about the laws of thermodynamics. And we're actually going to start with a law that's so basic, it was named after the first and second laws were already a thing. They had to go back and add it, calling it the zeroth law. It might sound a little like a logic puzzle, but this law is the reason thermometers even work. It's really just common sense, right? If A is the same temperature as C, and B is also the same temperature as C, then A and B have to be the same temperature as each other. This is exactly how a thermometer works. The thermometer is C. It matches the temperature of whatever it's measuring. And because of this law, we trust its reading. Okay, now for probably the most famous law in all of physics, the first law. You've definitely heard this one before. Energy can't be made out of thin air. And it can't just vanish. It can only ever change its disguise. Like when you rub your hands together to warm them up, you're just converting the energy of motion into heat energy. The total amount of energy in the universe stays exactly the same. And if we write it as an equation, it looks like this. The heat you put into a system, that's delta Q, has to go somewhere. It only has two options. Either it increases the system's own internal energy, delta U, basically making its molecules wiggle around faster, or it gets used to do work, delta W, like pushing a piston up. That's it. Those are the only two places it can go. Here's a really simple way to wrap your head around this. Imagine someone gives you some money. That's your heat supplied. You go and spend most of it on groceries. That's your change in internal energy. And the little bit you have left over, well, that's the work you can do. See? The budget has to balance. Every single bit of that energy is accounted for. It's a perfect balance sheet. So these laws are cool and all, but so what? How do they actually, power our world? Well, this is where it all comes together. This is how we connect the physics to the machines that define modern life. So every single heat engine out there, I don't care if it's a 19th century steam train or a modern nuclear power plant, they all follow this exact same three-step plan. Step 1, suck in a bunch of heat from a really hot source, like burning fuel. Step 2, use some of that heat to do useful work. And step 3, and this is the one people forget, you have to dump the leftover waste heat into a colder place, like the air around us. So the actual useful work you get out of the engine is just what's left over. It's the heat you put in at the start, minus the heat you were forced to throw away at the end. And as we're about to find out, that waste heat, that Q2, is completely and totally unavoidable. And check this out. If you take this whole process and just run it backwards, you don't get an engine. You get a refrigerator.
An engine lets heat flow naturally from a hot place to a cold place to create work. But a fridge, it uses work, your electricity, to force heat to move from a cold place to a hot place. It's literally pumping the heat from inside the fridge out into your warmer kitchen. It's the same physics, just in reverse.
This all leads us to a really big question. And it's our final topic. If we're so good at turning heat into work, could we ever, perfect it? Can we build an engine that doesn't waste anything at all?
Let's just ask it straight up. Is it possible to build a heat engine that is 100% efficient? An engine that takes every single drop of heat energy and turns it into useful work with zero waste?
The laws of physics give us a very clear, very simple, one-word answer. No. Absolutely not. And this isn't just an engineering problem we haven't solved yet. This is a fundamental, unbreakable speed limit of the cosmos. And here's the reason why. For that engine to be perfectly efficient, that waste heat we talked about, that Q2, it would have to be zero. All the heat you put in would have to become work. But the second law of thermodynamics steps in and says, nope, can't do it. It flat out forbids it. It says you must lose some heat to the cold place. There is always a tax. This right here is the official wording, named after the geniuses Kelvin and Planck. It's a fancy way of saying you can't just build a machine that sucks heat from one spot and turns all of it into work. It's impossible. You have to dump some of that heat somewhere else. Perfection, it turns out, is against the law.
So let's just nail down these takeaways. First, every single time you try to turn heat into work, you have to pay a waste heat tax. You just do. Second, because of that tax, no engine can ever be perfectly efficient. And third, this isn't just a suggestion, it's a fundamental rule baked into the very fabric of our universe.
And that leaves us with one final, totally mind-bending thought. If every single energy transaction in the cosmos, from a star burning to you blinking your eyes, creates some unavoidable waste heat, if it's always increasing the total disorder or entropy, what does that imply for the ultimate fate of the universe itself? That's a question that takes thermodynamics from inside your car's engine all the way to the very edge of cosmology. Something to chew on, right?
Thank you for watching my video. Please like, subscribe and hit the bell icon.